Thanks, Christoph. James is going to plug in here. Good. So we're now on to a set of 3 shorter talks. These are 15-minute talks, and we should be strict with our timekeeping. James Noble is going to talk to us about abstract syntax trees and why you should look for them everywhere.
Yes, well, actually, no, it's not about why you should look for them everywhere, but I'm pleased to be giving a short talk. Unfortunately, I'll have to dash next door to something straight afterwards. Yeah, flexible ASTs are fast and easy for flexible embedded interpreters. In the beginning, as we all know, there was Lisp. And if you're building a Lisp, you have to build a Lisp reader. And, you know, I encourage you all to forget about everything that Racket and Rhombus has taught us and about reader macros and macros and syntactically pure macros and macros in a syntax that almost look as if it could have been designed by, I don't know, Niklaus Wirth in 1970. Because really what you just have to hard code the bloody Lisp reader, and even if you look at what the Racket guys or the Rhombus guys are doing, they use that to bootstrap the system, and then they bootstrap on top of it, and they bootstrap on top of it, and eventually get their wonderful pile of macros. Smalltalk, well, in the beginning from Smalltalk, I do like Smalltalk. This picture is kind of irrelevant, but I thought it was funny. Because it talks about parser franchises. The Smalltalk parser is built into Smalltalk. In the image, which is basically a pile of steaming bytecodes that was originally written, I believe, in 1972, and then exported out of Smalltalk 72 and into Smalltalk 76, and then exported out of Smalltalk 76 into Smalltalk 78, which uses the same bytecode format as Smalltalk 80, which uses the same bytecode format that we run today, and you can actually go to a web page, I'm not going to, and load in an image into is it Peter Deutsch's? JavaScript interpreter of Smalltalk 78, I think it is, or some, in fact, no, Smalltalk 76, and you can run it there. And you just load up the bytecode and everything works. Right, for the young people in the room, which is almost everybody, there's Jason, right? If you want to load some random shit in, you just call Jason. So the problem we are facing, or have been facing, is we're developing this new language called Grace, which we would kind of like to bootstrap it. Well, when I say we, you know, because there's only 2 of us and we're kind of daft. Grace lets you write code like this, which means it does need a parser. In some ways, part of the design philosophy of Grace is that it's not that we hate macros, it's that we think that another level of indirection on the syntax just makes everything worse for almost everybody else. So, I'm sorry, there's a gentleman is giggling in the background. Excellent. This talk was actually a work-in-progress research talk, which means I have a feeling the program committee thought the entire paper was a joke. I was going to say, compared with the previous talks, there's the program committee, where the previous talks, which were about building something for a really huge, big commercial project, like, you know, I mean, Graal just starts for hotspot and then adds in piles and piles and piles of shit. This is kind of the opposite, because basically there's kind of none of us actually working on this project, and it's absolutely clear that having an awful lot of money, whether you're from a venture capital firm or from Sun or IBM, really helps your programming language projects. But, you know, to quote Ernst Rutherford, we don't have the money, so we have to think harder. We'd like to implement this. It's a teaching, or it was nominally, we called it a teaching language to justify working on it, because if we said, look, we'd just like to do a new minimal uninteresting object-oriented language, everyone would have thought we were crazy right out from the start. So what can we do? We're interested in this language, we're interested in running it on various platforms, which basically means hosting it in other languages. Well, after, I don't know, too long sleeping or too long drinking, we kind of realized this. Algol. And there's that snide comment on the side that says the one true algol is C. What I mean here is that, in fact, if you are extremely careful about the way you are choosing to, I guess, export or pickle or whatever word you want to use your ASTs, and in fact, you can't actually do it in the standard algol syntax. That's why I say the one true algol is C. You get something like this, which is obviously horrible. But the point of this is that it is syntactically correct without even running it through TR in a large fraction of all the programming languages you are ever likely to want to host this damn thing in. Maybe you've got to write a little bit of it. You do have to write some support code because those are the AST nodes, so you will have to do something to actually build the AST nodes. But if you're writing an interpreter, you've got to do that anyway. And if you're clever with a little bit of tweaking, you can then start loading in files like this, which means that we could have an awful lot of other stuff, including the Grace parser, including the Grace standard library, all these kind of things, particularly the parser, I guess, because once you bootstrap the parser, you can bootstrap everything else. And so this is syntactically correct in a whole lot of languages, and if you're willing to do TR, you can actually get to things like Pascal, which traditionally has different quote marks, and Smalltalk probably has different quote marks, and whatever. You can get to those kind of things with really very little effort. Prolog you can probably do. I don't think we have done. But that's really the point of the talk, okay? And I figure the paper got in because one of the program committee members, who hopefully isn't in the room, said something like, this is a completely daft idea, blah, 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 but maybe I'll use it in my next project. So I'm glad this got in because, you know, I often say, well, look, the best ideas are kind of obvious in retrospect. And I hope this idea is obvious in retrospect, and it'd be nice to have this paper out in the world so that if somebody else has a similar problem you want to, maybe this is student work. Maybe, for example, you're giving your student the exercise to say, well, let's write a toy little programming language. This would say, you know, you can give people these ASTs, and, well, either they can pass them in themselves, or what's even better is, when I say it's syntax, it's valid syntax across all these languages, I mean, it's valid syntax across all these languages. So you can just write the library code and you can link it against that. You don't even have to have a reader because you can just link it, these ASTs, directly into your source code in pretty much any language that you can think of. So everyone knows my background is object-oriented, so anyway, Michael is a more generous chap. But here's the Haskell stuff, basically. This isn't all the Haskell code you need. I can show that briefly if I don't run out of time, but that's basically it. There is a program, line 16 to 19. At the very bottom, you actually have to go off and tell the Haskell code to run it. These are the, well, I guess lines, the top lines here, cons and while and nil. Object, there's the definition of the object constructor. So we're actually defining a Haskell function that takes a tuple, which is a body, which is a recursive call on these things, and the annotations. And what this is doing is basically a bit of syntactic sugar using the C/algol/whatever calling convention, or what OCaml does, where you actually pass in a tuple, and then it's desugaring it into you know, something which is Haskell. We know it's Haskell because it's capitalized, and it doesn't have those parentheses, and it doesn't have any commas. And that lets us read this stuff into Haskell, and then, you know, down the bottom, I guess, there is an interpreter, which I think that's it, yeah, an interpreter from a context to an I/O. This is actually running something that is the interpretation of a number node. So you write the, you know, you write the interpreter like this, and then you can supply these ASTs and people can run it. So, you know, if were I to be giving an assignment to say write a code, write a program, a simple interpreter for something, I could give people all these ASTs and they can link it against their Haskell code or whatever else they want to link against, Java, JavaScript. But I'm not sure about OCaml does weird things with quotes. But anyway, a whole bunch of stuff. And they'll be able to run these test cases. So you could say, right off, write an interpreter in whichever language you like, we don't care. Here are the test cases. You don't have to write a parser, but you will be able to link them against pretty much whatever every language you pick. And if you can't link it against the language you pick, then don't pick that language. Do I mean any language? Well, it gets stupid, right? Simon Peyton-Jones isn't in the room. Alan Blackwell isn't in the room. They put Lambda and functions into Excel. Why? I don't know, because why would you want to? I mean, it's got its own extraction mechanisms and it's a spreadsheet, and it's not entirely convincing that having function definitions really helps you do anything with Excel. And I'm not even sure what Michael is actually doing here, but right up the top you can see, wow, okay, I've expanded it halfway down here. There is the same syntax, which is the syntax for the Grace program I showed you. And yeah, it's being loaded into Excel, and somehow it's spitting it out into various bits and pieces. I guess it's showing you the tree structure at least. Software visualization, sorry, that was my PhD. Right, represent. Okay, completely daft. Of course, when I mention all these languages that have syntax, fits into Grace syntax as well. So, you know, you can do this kind of thing where Grass pulls in the definitions for the nodes of the AST, for the Grace AST, and then, you know, we can write a program there, or we can pull it in from somewhere else, and we can run it, and we run it. I think I was supposed to finish at 5:05, was I? There'll be time for questions. There we go. This is a visualization done by cutting, and I did not use AI in any way in manufacturing this talk. Cutting and pasting the icons for all of your favorite programming languages. And you know, we will, if you would rather like to have your language on the slide, we'll accept money. Because I'm no longer at a university and I'm kind of looking for a job, and yeah, you know, I might be forced to go and work for a bank or something, but with the tax department in Wellington. But until then, I'm doing this sort of stuff. So yeah, we've got, what is it? All of those ones we actually have ASTs running for, and then, so we have the AST readers, and on the right-hand side we've got the languages where we've actually managed to, well, Michael has written the few pages you need for a Grace interpreter. So that's basically it. These kind of fast ASTs can be embeddable, fast and easy. And I've got a few minutes left for questions, or if you really don't believe anything I've said. Is that font big enough? Oh, sorry, it's done that thing, hasn't it? Now, I have to remember, oh dear, I pressed the wrong button. I don't know. There it is. I was going to say, I don't know which side of the screen this is, and now it's impossible to drive the mouse because it's backwards and I can't actually see what is going on that screen. But yeah, hello world. If you say, whoops, if I say produce the AST, well, I've already done that. There it is. Don't believe me. Whoops. Produce the AST. There it is. Hello, MPLR. There's the AST. If you execute it, if I can remember how to do that, there we go. It's actually run it and spat the thing out on the far right-hand side. And actually, I lie. In fact, this is directly connected to the previous talk, because the previous talk was precisely about things like ahead-of-time compilation that you can then run. So if you want to do an ahead-of-time compilation of this, you don't want to run a Grace interpreter, you'd actually run a Grace interpreter that's kind of wrapped up in standalone Java, so we're doing nested interpreters. This thing should generate, I'm told, there it is, a great big Java. And what's the important thing? The important thing is that, okay, there we go. There's a whole lot of those definitions. That's the definitions of the AST. That looks like a visitor to actually run the thing. It's horrible, isn't it? Right, and you know, then right down the bottom, I think, there's all the definitions. And, you know, it's one file, okay, bang. Oh no, where is it? Can't find it. Because, anyway, I think we're not right down at the very bottom. At the very bottom, what the hell is it doing? There it is, okay? There is that AST. And the important thing is, you know, well, I mean, it seems pretty obvious one could do this in JavaScript, but just to be clear, that looks very much like the thing. We're at the bottom. So there was a const program, I believe. There's the same program, exactly the same AST. And when we say directly incorporated into your source code, we mean directly incorporated into your source code, which is what we've done there. And the fun bit, of course, is it will think a bit, presumably. Is it still thinking? Probably crashed. I mean, this is written in some combination of Grace and JavaScript.
We should give you a round.
Thank you. Well, I then will dash to the next. Damn, Haskell. Was it a joke? No, but you know, you can just cut and paste. You can just cut and paste the thing.
Yeah, very good. Good.
Was it a joke? I don't know. Well, thank you once again, and I'm afraid I have to